Assalamu alaikum and good morning, everyone. So yesterday you have already looked at how to calculate the half-life, successive half-lives from the concentration time graph. We've also looked at how we can use the initial rate of reaction given the concentrations of each reactant and the effect of increasing, doubling the concentration and what effect it has on the initial rate of reaction. Okay, and as mentioned, if you want to determine the order of a particular reagent, for example, hydrogen, you need to choose at least 2 experiments that only differ or that only changes the concentration of the hydrogen. Okay, so we'll jump straight to the example. So we are to work out the rate equation, but before we are able to write down the rate equation, we also need to know what are the orders of each of the reactant, and we also need to know what reactants or what reagents are included or appear in the rate equation. So usually we look at the reactants. In this case, it's the A, B, and C. The reason for this is because the reactants are the ones that we can adjust. That means by adjusting, I mean changing the concentration and then taking the initial rate of reaction. Okay, so in order to calculate the order for a particular reactant, it is easiest to compare 2 experiments where only the reactant is being changed. So that particular reactant. I'll show you in a bit what I mean by this. Just a reminder to you that if changing the concentration, but the rate stays the same, then it is a 0 order. If we double concentration, the rate doubles, so that's directly proportional, and that means it is first order. If we double the concentration and the rate quadruples, so that means the square of the concentration, then the order is second order. Right, the first one that we are going to determine is easiest. We start with focusing on just A. That means we need to choose 2 experiments that only changes the value of A while keeping your B and C constant. And if you can spot this, if you look at experiment 1 and 2, the difference between experiment 1 and experiment 2 is that the concentration of A has been doubled. Okay, has been increased by 2, but keeping the concentration of B and concentration of C the same. So even though there are 4 experiments, we only just want to look at experiment 1 and 2 for now. So I will just highlight experiment 1 and experiment 2. So the concentration, maybe I do it here so you can see. Concentration for experiment 1 and 2, you go from 0.1 to 0.2, and the rate you go from 0.1 to 0.2 as well. Okay, so 0.1 to 0.2 for concentration is an increase by times 2. Okay, how do I know that? You just take the bigger number, 0.2 over 0.1, and that is a multiple of 2. That means you multiply the concentration by 2, the rate is also multiplied by 2. So because the increase in concentration is the same as the increase in rate, therefore, the order with respect to A is first order. Okay, because When you double the concentration, the rate double as well. Okay, when concentration of A is doubled, rate doubled as well, which is already written down for you in that box. But I think the most important thing for you is this working, okay, to multiply, to show that it is being multiplied by 2. Okay, moving on. Now we want to find the order for B. Okay, so we need to choose 2 experiments that only changes the concentration of B while skipping your A and C constant. And I can see that experiment 1 and experiment 3, the concentration of A is constant, same. The concentration of C is also the same, and you are only changing the concentration of B going from 0.5 to 1.0, okay? If we write this down, concentration goes from 0.5 to 1.0, and that is a multiple of 2 times 2. And the rate at 0.5 is 0.1. The rate at 1.0 is 0.4. So you take 0.4 divided by 0.1, that increase in rate is times 4. So you can see that concentration goes up by a factor of 2, rate goes up by a factor of 4. Times 4 is the same as writing it down as times 2 squared. Okay, it is the square of the increase in our concentration. Because of this, reactant B is second order. Please make sure you copy this down so you know what I'm talking about. If you are already comfortable with this method, I usually would just write it down here. Going from 0.5 to 1.0 is times 2. Going from 0.1 to 0.4 is times 4. So you can see that times 4 is also the same as times 2 squared. And when you increase the concentration, the rate goes up by the square of that concentration. So we've got our order for A, we've got our order for B. Lastly, we would like to have a look at our order for C. Okay, so again, we have to choose 2 experiments that only changes the concentration or only have different concentration of C while keeping your concentration of A and concentration of B the same. Okay, so you can see that is experiment 1 and 4. Our concentration of C goes from 0.25 to 0.5, and the rate stays the same. So if I were to write down my working, concentration of C goes from 0.25 to 0.5, and that is a multiple, an increase in by a factor of 2. Rate goes from 0.1 to 0.1. So rate stays the same. Okay, because increasing concentration does not have any effect on the rate, this implies that C is 0 order. or if you can already spot it from here, that's an increase by 2. This one, no change. And I'm only focusing at experiments 1 and 4. So overall, the order with respect to reactant A is 1, the order with respect to reactant B is 2, and the order with respect to reactant C is 0. I have to write down the rate equation, where rate equation is equals to K times the concentration of A to the power of its order, which is just 1, times by the concentration of B to the power of its order, which is 2, times the concentration of C, which raised to the power of its order, which is 0. So if I tidy this up, rate is equals to K times concentration of A times concentration of B squared. Anything to the power of 0 is just 1. So this is how you work out the order of the reaction. And as you can see, the concentration of C, or the species C, does not appear in the rate equation because it is raised to the power of 0, or we say that it is 0 order. So since it's 0 order, it doesn't have any effect on the rate of reaction. Okay. Right. In most questions, it is possible to compare between two experiments where only one reactant has its initial concentration changed. If, however, both reactants are changed, then the effect of both individual changes on concentration are multiplied together to give the effect on rate. And this is what we mean by combined effect. Okay, I'll show you what I mean by combined effect in the next example. Okay, I think, right, I missed something out here. I'm supposed to find the rate constant, okay? So going back to example 1, sorry about that. I will have another section here to find the rate constant. So we want to find the value of K. As you can see here, the overall order of this reaction is 3. Okay, so the reason why I point that out is because you need to know the overall order of the reaction to find the units of K. Okay, so how can we solve what K is? So K is equals to concentration of A times by concentration of B squared over the rate of reaction. Because K is a rate constant, it is constant regardless of what concentrations you use. So you just have to pick out any one experiment. Either you use experiment 1 or experiment 2 or experiment 3 or experiment 4, you will get the same rate constant because we assume that these different experiments are carried out at the same temperature and pressure. Concentrations, initial concentrations, do not have any effect on your rate constant. Only temperature will affect the value of your rate constant. Okay, so you can choose any one of the experiments that you would like to use. Oh, okay, actually this is example 1, right? It doesn't ask for the rate equation and the rate constant actually, but anyway, since I'm already here, I will just continue. So, okay, we will use experiment one, but if you want to use other values, then that's fine. Concentration of A is 0.1 times concentration of B is 0.5 square over the rate, which is 0.1. To work out the units, you know you've got mole per dm cube times mole per dm cube square on top over rate is mole per dm cube per second. And if we cancel this out, we get mole square dm minus 6 as minus 1. And then you just have to work out this number. And don't forget the units. Okay. So whatever this number is mole square dm minus 6 s minus 1. Sorry, it's s plus 1. So because when I carry it up, it becomes positive. Okay, or just second, it's fine. Whether you leave it as just s or s to the power of 1, that's fine. Okay. Right, back to this combined effect. It will be shown to you in example 2. Work out the rate equation for the reaction between X and Y using the initial rate data in the table. So the equation is not given to us, and that's fine because we do not need the equation to work out our rate equation. We do not need the chemical equation to write down our rate equation. Let's start with reactant X. For reactant X, I think we can use experiment 1 and experiment 2 because our concentration of Y is constant. Do I have space here? Okay, here, sorry. So experiment 1 and experiment 2, because the concentration of Y stays unchanged. And the only thing that's changing is the concentration of X. So you can see the concentration in experiment 1 is 0.05. In experiment 2, it's 0.1. So that means there is an increase in concentration by a factor of 2. Concentration goes from 0.05 to 0.10. And that is an increase by 2. Again, if you're wondering, how do I know? Well, this one you can easily see. If it's not a nice number, you can take the bigger number, divide by the smaller number. And the rate goes from 0.15 times 10 to the power of minus 6 to 0.30 times 10 to the power of minus 6. So again, you take the bigger number, divide by the smaller number, and that is an increase in 2 as well. So you can see that concentration increases as the rate increases at the same factor as the concentration. So we can say that X is first order. Okay, the explanation to that is as concentration of X doubles, the rate doubles as well. Therefore, the order with respect to X is first order. Okay, so that's X done. Just remember that X is first order. If you need to copy this down, please pause the video now. I will move on to the next one. Now for reactant Y, okay? I need to choose two experiments that only change Y, but you know that is not possible, okay? You take one, you cannot take 1 and 2 because the concentration of Y is the same. So there's no change in concentration. You can't comment on the change in concentration. You can either take 1 and 3, okay, which is sorry, for experiment 1 and 3, both the concentrations of Y are changing and the concentration of X are changing as well. For experiment 2 and 3, same thing. The concentration of X are changing and the concentration of Y are changing as well, okay? But that's okay, right? Because we don't have any choice. We just have to pick two experiments, okay, whichever you want, remembering that X is first order. We need to combine the effect, okay? So let's just take 1 and I'm going to take 2 and 3. Okay, so 2 and 3, my X is also increasing by 0.2 divided by 0.1 is a factor of 2. My concentration of Y is also increasing by a factor of 2. And then you can see here 2.4 divided by 0.3. This is an increase increase in 8 times. Okay, so let's see. How do we do this? The concentration increase for X 0.1 to 0.2, which is, and for Y, it's also 0.1 to 0.2. Okay, and that increase is times 2. This is also times 2. So the combined effect is the rate goes from 0.30 times 10 to the power of minus 6 to 2.40 times 10 to the power of minus 6. And this increase by a factor of 8. We know already that X is first order. That means increasing the concentration of X by 2, my rate should increase by 2 as well. So I can break down this 8 into times 2, and the remaining is times 4. Okay, times 2 is the effect of X. And that means times 4 must be the effect of Y. Okay, so you can see that as I increase Y times 2, the rate increase or goes up by 4, which is 2 squared. This suggests that Y is second order. Okay, I repeat. The rate for between experiment 2 and experiment 3, sorry, for experiment 2, the rate is 0.3 times 10 to the power of minus 6. And then for experiment 2, 0.3 times 10 to the power of minus 6. Experiment 3, 2.4 times 10 to the power of minus 6. And that is an increase by 8, a factor of 8 or a multiple of 8. Okay. But in experiment 2 and experiment 3, you are not only changing the y from 0.1 to 0.2, you are also changing the x, which is from 0.1 to 0.2. So this times 8 is actually the effect of changing both x and y. This is what I mean by the combined effect. However, we already know that x is first order. So if I increase my x by 2, my rate should also go up by 2. That means this times 8, I break it down, okay, into the individual effect of x, which is times 2, and the remaining must be the effect of doubling the concentration of y. Right? So as you can see, as x doubles, the rate doubles as well. As y double, the rate quadruples. So this is how we can conclude that y is second order. Okay. Okay, so compare between experiment 2 and 3. So compare experiment 2 and 3. The rate goes up by a multiple of 8, which is times 8. We know x is first order. Therefore, when concentration of x is double, the rate doubles as well. The effect of y on the rate must be to quadruple it. Okay, so our last statement, space, as concentration of y double, the rate goes up by 4. And 4 is the square of 2. Okay. Sorry, this first order, actually, I was referring to my x. So please move that, otherwise you will get confused. Therefore, y is second order. I don't know where else I can include that statement. Maybe here. Therefore, y is second order. If you need to copy this down, please screenshot the slides now, or pause the video or take a screenshot now. I will move on to writing down the rate equation in the next slide. So to write down the rate equation, its rate equals to rate constant times by the concentration of X, since it's first order, to the power of 1, times by the concentration of Y, since it's second order, it's to the power of 2, or we say squared. Next, I want to work out the rate constant using this rate equation. Again, you just choose any one experiment, whether you want to use the data for experiment 1, experiment 2, or experiment 3. Remember that if you choose experiment 1, you have to use all the data from experiment 1 only. You cannot mix and match and say, oh, I'm going to use the concentration of experiment 1 for X, and then for Y, the concentration for experiment 2, and then the rate somehow you use experiment 3. Okay, so that is not right. I am just going to choose experiment 1. Rearrange K, it should give me wait, did I is that even correct? It should be the other way around. Sorry. This should be the other way around. Oh gosh, I just realized that now. So that means this whole thing is wrong. Okay. So rate constant is K equals to rate over concentration of A times by concentration of B squared, and rate is mole per dm cube per square minus 1 over mole per dm cube and times mole per dm cube square. So that cancels out. You should get mole minus 2 dm6 as minus 1, and you should get a number here. Okay, so please correct example 1, and then we go back to example 2 to find the rate constant. So sorry about that. I just realized K is equals to rate over concentration of X times by the concentration of Y square. Choose an we're using experiment 1, 0.15 times 10 to the power of minus 6 over 0.05 times the square of 0.1. To work out the units, mole per dm cube per second over same thing, mole per dm cube times by mole per dm cube square. And you cancel this out. You should get mole minus 2 dm6 s minus 1. And you should work out the number. Okay. So remember, the K is the same for all experiments, whether you're using experiment 1, 2, or 3, as long as the temperature is the same, because we know that the value of the rate constant K is only affected by temperature and not concentrations. Okay, if you need to copy this down, please pause or take a screenshot. Example 3, find the rate constant K. The progress of the reaction can be followed by measuring the initial rates of reaction using various initial concentrations of each reactant. Okay, we are already given the rate, right? So this is something that was already mentioned in your I don't think it was mentioned in your question paper. Yeah, no. The rate equation is given to you. Otherwise, if you want to work it out, you can work it out quickly, okay? Just to prove that the rate equation we're given is correct. So looking at experiment 1 and 2, you can see that the only the concentration of calcium carbonate is changing. So I will take 0.0250 divided by 0.0375, whatever the bigger number is. Is it correct? 0.0375 divided by 0.0250 is, oops, times 1.5. This is not changing, and I need to know how much my rate has increased. 6.63 divided by 4.38. That is also increased by 1.5. Okay, so that means since the concentration of calcium carbonate increases by 1.5 and the rate increases by 1.5, so the order of calcium carbonate is 1. Okay, correct. And then I want to look at the concentration of Cl minus, and H plus is not in the expression because the order is 0. Okay, so we know that this is first. We don't know this at the moment, and this is 0 order. So I'm going to use a different color now. If I want to study the increase in concentration of chloride, I will take these two equations. So that's 0.0250 divided by 0.0125. And that is an increase by 2. Okay. If you notice that the calcium carbonate is now decreased in value. So I will take whatever this number is, 0.00625 divided by 0.0375. Why have I taken the smaller number divided by the bigger number? Because I want to follow my chloride. Okay, chloride, I take bigger number divided by smaller number. So that means for calcium carbonate, I must take the number from experiment 3 divide by the number from experiment 2. And I know that the increase in H plus will not change my rate. Will not affect rate. Okay, so if I look at my rate, I go from 2.19 divided by 6.63. That is a decrease in 0.33. Okay, and this 0.33 is a combined effect for effect of X, and the other one is effect of Y. Since X, calcium carbonate and chloride. Sorry, effect of calcium carbonate and effect of chloride. So since my calcium carbonate is first order, increasing the concentration, or rather here decreasing, but increasing by 0.16 means I would also increase the rate by 0.16, okay? My total decrease or increase for that matter is 0.33. So I need to take 0.16 out of the 0.33, okay? So that means 0.33 divided by 0.16 is 2 times 2. So times 2 is the effect of increasing the concentration of chloride by 2 as well. So can you see that as I increase the concentration of chloride by 2, the combined effect is also increasing the concentration of chloride by 2, which confirms that chloride is also first order. Okay, so this is not, it's still easy. I mean, it can be done, but because they're not a nice number, as you can see, we have 0.16 here, okay? But because it's first order, if you increase or decrease by 0.16, the rate must also decrease by 0.16. Okay, right, but that's not the question actually. If you want to copy this down, I suggest you to pause this video here and then see for yourself if you can agree with the fact that calcium carbonate is first order and chloride is also first order. Hydrogen plus does not appear in the rate constant. That means it must have been a zero order. Okay, then the real question is to find the rate constant given the rate equation. So K is equals to rate over concentration of calcium carbonate and concentration of chloride. Again, you just have to choose one experiment. Choose experiment 1, maybe. Okay, so K is equals to 4.38 times 10 to the power of minus 6 over 0.0250 times by 0.0125. And to work out the units is mole per dm cube per second over mole per dm cube times mole per dm cube. The mole per dm cube cancels out nicely. So you should get your unit as mole minus 1 dm cube as minus 1. This is the units for the rate constant K for an equation with an overall order of 2, second order. Okay, you add 1, 2, and this one is 0. Okay, so work out the number for that. And we should, okay. So again, you can choose experiment 2 or experiment 3 as long as you don't mix them up. Okay, if you use experiment 2, stick with experiment 2 and always only use the values from experiment 2. Likewise with experiment 3. Next, rate constant. Calculate the numerical value of a rate constant For example, by using the initial rates and the rate equation using the half-life, and the equation K equals to 0.693 over T half. So if you're wondering what 0.693 is actually your ln2. Let me just check that in the calculator. Yes, it's 0.693 1471806, but your learning objective is okay with just 0.693. Okay, the rate constant can be calculated from the half-life of a reaction only and only for first order, because first order is the only type of reaction that has a constant half-life. The formula is ln2 over K, or you can write it down as 0.693 over K, and you just rearrange it. Okay, let's try. A first order reaction has a rate constant of 9.63 times 10 to the power of minus 5. Calculate a value for half-life of this reaction. So it mentions a first order, so that means you can use T half is equals to 0.693 over K, 9.63 times 10 to the power of minus 5. And this is S minus 1. The unit would be in seconds because you bring up the S minus 1. Okay, please work out the numerical answer for that. It is pretty straightforward. So I'll move on to example 5. This time the rate is given, K times the concentration of cyclopropane, and so that means cyclopropane is first order, okay? Because the square bracket is to the power of 1, you want to find K is equals to 0.693 over T half. Now the question is, well, the question doesn't say if they want the answer to be in second or in minutes, but to be safe, we convert our minute to seconds, okay? And that should give you the answer, since T is in second, as minus 1. If you do not want to convert, you can also leave your answer in minute minus 1. Okay, so it depends on which one you want to choose. If second, you need, if you want your rate constant K to have a unit of second minus 1, you change your minute to second. If the unit of K, the rate constant, to be in minute minus 1, then you just take 17 minutes. Okay, work that out, and then the answer later on, you can put it in the forms. Lastly, okay, last for this lesson, the effect of temperature on rate constant. Describe qualitatively the effect of temperature change on the rate constant and hence the rate of reaction. Okay, so this is nothing new for you. Increasing the temperature will increase the value of rate constant K, hence the rate of reaction increases. Changing the concentration will not affect the rate constant. The value of the rate constant is affected by change in temperature or the addition of catalysts. So if you change the activation energy, this will affect the value of your rate constant. An increase of 10 degrees Celsius approximately doubles the rate of reaction. So you don't have to worry about that because you only have to understand qualitatively. So you don't have to quantify. Okay, so that is all for today. Don't forget to fill in the forms. Most of the question in the forms are just asking for numerical answers for the examples that we did earlier on. And make sure that you submit the forms by 4:30 p.m. today. Thank you. I don't know how long this video is, but thank you for staying through. And please make sure to amend the mistake that I made just now. It was a major mistake where I incorrectly rearranged my rate equation. Okay, sorry about that. All right then. Thank you everyone. Assalamualaikum, and yeah, have a good day. Bye.